All right. What we're getting into with this is let's look at what are known as the empirical gas laws. Okay. Empirical means based on experiment. So we're going to be looking at things, uh, gas laws that were based off of experiments. And again, this is a lot of where chemistry started. Okay. Um, so let's dive into it. There are three of these we're going to talk about, but there's probably a bunch of them. Okay. We're trying to stress too hard about them as we go. All right. First up is Boyle. I stole this blurb from Wikipedia. It's just a little bit of information about Boyle. This is Boyle. This is actually a painting of him in 1689. Okay, painted by this guy. Anyway, uh, Boyle. Boyle's law says that a volume of gas is inversely proportional to its pressure. What does that mean? This is at constant temperature in moles. So at constant temperature in moles, what we're saying is inversely proportional means that the volume of the gas is directly related to 1 over the pressure. Okay, this is inversely proportional. So one way to phrase this is to say that the pressure times the volume should be equal to a constant. Okay, which means we could also say that P1V1 equals P2V2. Okay, so if you're comparing two gases at the same temperature with the same amount of moles, you could do P1V1 equals P2V2. Okay, I'm not going to say this is ideal to be doing, but this is a reasonable way to do it because Boyle's law should work. Okay, uh, this is just more things. Boyle's law is how breathing works, right? Your diaphragm controls the volume of your lungs, which is controlling the pressure. So as the pressure decreases, your lungs have to take in more air and the volume increases, and so on. Okay, we can see it here. If we plot 1 over pressure versus the volume, as the volume increases, 1 over pressure increases, which means the pressure is decreasing. That's what this means. That as the volume increases, the pressure is decreasing. Okay, that's what Boyle uh, was pointing out for us. Okay, the next one is Gay-Lussac's law. Um, this is sometimes also known as Charles's law. I learned this as Charles's law. Charles's law and Gay-Lussac's law are the same idea. Charles is actually no, I have it backwards. Gay-Lussac is the one that is credited with it, but Gay-Lussac cites Charles in a lot of his work and said all of this is based off of things that Charles did, even though, yeah, okay, anyway, there we go. So it's both of them worked on it together, not together, but at different times, because I think they didn't even live at the same time. But Gay-Lussac based all his stuff on Charles's work, and so he credits Charles with a lot of this discovery, and so they both have their names on this. Okay. Uh, Gay-Lussac is telling us that the volume of gas is directly proportional to its temperature. This is Kelvin temperature. Again, oh, that's not a good match. Let's do this. Kelvin temperature at constant temperature and pressure. So we can say that the volume is directly proportional to the temperature. Okay, which would mean that the volume divided by the temperature is a constant. So if we were comparing situations, we would say that V1 over T1 is equal to V2 over T2. Again, we're not going to have to do it that way, but you could do it that way if you knew that the pressure and the moles were going to be constant. Okay. If we look at some data, right, this is saying that as the volume, right, as the temperature goes up, the volume goes up if you're at constant pressure, right? You probably noticed this with your tires in your car, right? As it gets cold in the winter, when it first starts to get cold, the atmospheric pressure is roughly the same, but the temperature has dropped a lot. So the pressure in your, not the pressure, the, never mind, this is pressure temperature is something else. The pressure goes down, right? Because your tire doesn't change its volume. But anyway, whatever. Um, anyway, what's interesting about Gay-Lussac's law, right? As we increase the temperature, we increase the volume, right? We see that here, some data as we do that. If you take this data and extrapolate, which means continue doing it past where you collected data. So that's what this second plot is. This is where we stopped collecting data. But if you extrapolate these lines all the way back until they hit the x-axis, they all hit the x-axis at the same time. And the x-axis says negative 273.15. This is at 0 volume, okay? So 0 volume is kind of not really achievable, right? This is the physics, not physics, a physical thing, okay? But what it tells us is 0 volume at negative 273.15 Celsius. This defines our temperature of 0 Kelvin, or absolute 0, okay? At absolute 0, all of the motion of stuff has stopped. There's no more kinetic energy there, okay? So with all motion stopped, there's nothing there to measure the temperature. That's the coldest temperature possible. Okay. Yeah, and that's just extrapolated through Gay-Lussac's law. Okay. The third empirical gas law I want to look at is Avogadro's law. We know Avogadro. Avogadro brought us the mole and his number. Hopefully you remember Avogadro's number, right? 6.022 times 10 to the 23rd. Okay. And Avogadro told us that the volume of gas is directly proportional to the amount of gas that's present in terms of moles, as long as we have a constant temperature and pressure. Okay. You know what? Let's just do orange. All right. So what they're saying here is that volume is orange looks bad. Let's do yellow. I like it yellow. Here we go. Volume proportional to N. N here is moles. Okay. Which is telling us that the volume divided by N is a constant. Okay. So if we were comparing, we could say V1 over N1 equals V2 over N2. Okay. We can look at some data here, right? And really, this is not so bad and this should make sense, right? If you have twice as much moles of stuff, the volume should increase twice, right? It should be increased. There should be a direct correlation between the volume of stuff and the moles. So we could even go so far as to say that we could interpret our gas reactions in terms of volume. This only works because all three reagents here are gases. Okay. So because all these things are gases, this works. Okay. We're not going to do it that way, but this is where this comes from, right? Measuring the volume of stuff with moles of gas. Okay. These are our three gas laws. We can kind of think about them. We're not going to use them for anything. The next video is going to show you something much better that we're going to use to do this. Okay. But there they are. And know the names and some other stuff. We'll be okay. All right. I'll catch you in the next one. Let me know if you have any questions or issues.